Hello everyone, I'm Ashraf, and today I'll be presenting my work with Roberto Gayosa from Pacific Northwest National Lab. This presentation is part of 13th ACM Spec International Conference on Performance Engineering. This work looks into hardware design space exploration for application from an application perspective. We are in the golden age of computer architecture. At this point, there are multitude of accelerators which are coming out, driven by the needs of the machine learning domain. In this work, we are looking into how the architecture for these machine learning accelerators can be influenced such that it is beneficial for other kind of applications as well. Uh, this is a hardware software. This work presents a hardware software co-design approach, and it is meant to be agile and looks at applications with realistic input sets. The idea here is that we are looking into the future where the nodes will become more complex, where specifically you may have programmable devices such as CPUs and GPUs next to domain-specific accelerators, where some accelerator may be doing some sort of gem accelerations, some may be doing FFT acceleration, so on and so forth. Uh, so how do you design such system nodes? The use cases might include where you might have a HPC application with a machine learning component. For example, you want to scale molecular dynamic simulations, atomic simulations beyond a certain number of atoms, and you can do this using graph neural networks, for example. There's also a use case where your HPC applications are generating data, and that data analytics can be performed in parallel as the simulation is running. This is an opportunity to do hardware software co-design, and this work presents a particular flow which enables you to do an application aware hardware software co-design. You want to make your application more performance efficient or more reliable. Depending on the needs, you can target these goals and move forward from there. You may want to decide how many type of how many and what type of accelerators you want to put in your system node, and what kind of benefits do you obtain by putting these kind of accelerators on a single node. Uh, uh, at the same time, these systems are supposed to be heterogeneous with multiple software stacks and of course multiple hardware devices. How do they interact with each other? What is the end-to-end application performance? How do you program these devices, and how does resource scheduling work, and what kind of overheads it brings to the table? All of this can be explored using the proposed framework. Uh, uh, Here, we present in the software stack, plus as well the sitting on top the hardware we propose to work on. So the idea is there's a Minos computing library sort of layer which acts as a programming model as well as a scheduler, which schedules tasks on these available hardware devices. And your system is here composed of real hardware devices where it may be CPUs, GPUs, FPGAs, uh, and then sitting in parallel with this is an emulated hardware device which sort of simulates functionality of these fixed function accelerators. We call this Proteus device, and the functionality for this could come from multiple hardware accelerator simulators. Minos Computing Library, or MCL, is a framework for programming heterogeneous systems. It is an asynchronous task-based programming model and runtime, and it orchestrates compute and data among available devices. Proteus device is implemented as an OpenCL device, and it is implemented using the Vocal library. So once a Proteus device is instantiated, it is visible at a system level as an OpenCL device, as shown in this screenshot. What is a Proteus device? So this gives a basic overview of a Proteus device. Proteus is a data parallel compute device. Essentially, it has multiple compute units, and each compute unit is operating in parallel. Uh, Here, a single compute unit is designed uh, to implement a fixed function. And the idea is that you run offline simulations to obtain performance estimates for the execution of the kernel on this particular compute unit. And you plug in these numbers into this simulator, and it gives you this performance estimate from an end-to-end application perspective. Uh, of course, there are the other parameters which are also tunable, like the data rates and the kernel launch overheads and so on and so forth. This gives an example of a simple functionality of a Proteus device, where you have the host side here on this side and the accelerator on this side, the Proteus simulated device on this side. And this Proteus device is simulating compute units, where each compute unit is capable of performing 64 by 64 gem, and each compute unit is capable to run in parallel. So on the host side, what we have done is we have created an application where we need to maybe perform a very huge sized gem matrix multiplication. At the application side, we have divided this into tiles of 1024 by 1024 gems. And these T tasks are then passed on to the MCL scheduler. MCL scheduler will schedule these tasks and pass it onto the Proteus device. So this goes into the kernel queue for the device, and then work from the kernel queue is decomposed into units of work which can execute on the compute units. And then this work queue is populated, and compute units will then take work from this work queue and start working on that work. Once they're done, they go back to the work queue. If there's work available, they take, and so on and so forth. This figure shows a design flow where one particular way of doing design space exploration, where you might have multiple applications and they have different kernels, and maybe there is some overlap of different kernels, here ABC XYZ. And then you have these a couple of simulators, hardware accelerator simulators, where these hardware accelerator simulators uh, only do a simulation of kernels ABC, and this hardware accelerator simulator does simulation of kernels XYZ. You do some design space exploration within the hardware accelerator. You obtain some design points, and then these design points are used to populate config files with the Proteus device. The runtime environment is set up, the scheduler is run, and the apps are run, and then metrics of interest are gathered. And if there's a need, you sort of reiterate in this design cycle. So this is a deep dive into this different steps. So step one, you have written an application where this is described in the MCL programming model. It is sort of a low-level programming model, but the idea is that this code will be generated automatically from a high-level coding from a high-level language. And if you're familiar with OpenCL, there is a lot of similarity here where you create a task, you set the kernel, and here you're saying that this is supposed to be done on the fixed function accelerator. So there's no need to provide the kernel code, which needs to be compiled at runtime. Then you set the arguments, you execute the kernel on this Proteus device. So step two here is you do some hardware exploration of hardware accelerated design space, and you can use multiple simulators here. I have given an example of Aladdin, which is a pre-RTL simulator. Essentially, you provide your kernel you want to accelerate in C code. That's an LLVM IR trace is generated from this, and then this data flow sort of graph is determined from that based on factors such as loop unrolling. In this case, we have said unroll the loop by a factor of 2. So these two paths can operate independently. And the idea is that you obtain the number of cycles needed to complete this operation. This is another example of time loop where there's a different way of doing things, but your processing elements are sort of defined. You map this problem, which is described in the manner of loops, onto this uh, onto this architecture and do design space exploration. After these experiments, one can obtain these number of design points, which is exploring trade-offs between power, performance in area or performance of power, and pick a certain number of design points to move forward. You once these design points are obtained, you populate the config files. You set up okay, how many number of compute units to put in a single device. What are the different parameters such as data transfer rates. You set up the kernel signatures. You specify the execution latencies in these config files. Then you set up the environment through environment variables. You say here in this case, you're setting up two Proteus devices. And this is the part of the config files for these Proteus devices. You run the MCL scheduler, you run the applications, and at this point you obtain performance numbers for your applications. And if things work out well and good, but if you need to reiterate, you can try different design points, in meaning you can put different config files, or you can try different system configurations, meaning maybe you want to try with 4 Proteus devices. Uh, so you can do this, all of this, without needing to rewrite your application or recompile your application. So this is an example flow where one might take, but this is just what we have done for the experiment for this work, uh, demonstrating this workflow. We have chosen a few applications from HPC and graph domains. So CCSC is a computational chemistry application, and it has tensor contraction, which is decomposed into transpose, gem transpose. So the major kernel here is a dense gem, which needs to be accelerated. Similarly, triangle counting is from graph domain, and it is the major kernel here is sparse matrix multiplication. So we in this work we tried different simulators, and essentially these will some simulators will work for dense kernels, and some will only work for sparse kernels. And based from the running these simulators, we obtain these design points, which we try next in our work. So in this setup, what we are trying to do is we're trying to obtain what is the performance benefit of using these domain-specific accelerators. So our baseline in this case is a DGX V100 NVIDIA, which contains 8 NVIDIA V100 GPUs. So that's our baseline, and we want to see how much better performance we can obtain by including these 50% of new domain-specific accelerators and see what benefits we obtain. So these are some of the results. So for dense and this is overall application performance, end-to-end application performance. So thinking about Amdahl's law, what is the serial part of an application, what is the parallelizable or accelerated part of an application. These are some of the numbers we obtain, and here each design point here from a different simulator means the latency of performing one specific compute unit operation is obtained through these simulators. Uh, and we can see that for dense application, this particular case, we have high speed ups, and for sparse, we have a little bit of less speed ups. Another thing which we can explore using this framework is, let's say how many compute units you can put on a single device. So here we see adding too many compute units has diminishing returns. This is an example where we are comparing two designs, where one design is 32 times slower than the other design. So this causes that these domain-specific accelerators take a lot of time to go through these tasks. So this axis shows the number of tasks, the total number of tasks based on the input size. So because these are taking so much time, then these tasks start to spill over onto the GPUs, and that results in significant slowdowns. So this is another result which is showing how the system is being utilized. Here we can see for the dense case, we reach up to 100% system utilization for some inputs. So again, these are the number of tasks being generated at the MCL level. And here we can see that for sparse cases, we don't achieve full utilization of the system. So there is an opportunity to get better performance, but with even fewer devices. This is a result where there's again an aspect of data communication where for sparse kernels, the average data transfer tends to be lower as compared to dense kernels. So in conclusion, the proposed work is a coupled simulation methodology to explore next generation system nodes uh, in an agile manner for applications based. So developers can go ahead and design system nodes for their desired architectures. It's a easy and flexible system to framework to use. You can quickly explore different architectures based on your application domains. At the same time, this gives you the ability to run in conjunction with real hardware devices. So that's another positive aspect of this work. This programming model, the MCL-based programming models enable hardware software to co-design for domains ranging from embedded to high-performance computing, in the sense that you can constrain yourself in the number of compute units on a single Proteus device based on your requirements of maybe low power for embedded case as well. So this slide acknowledges some of our collaborators at Sandia National Laboratories and Georgia Tech and the funding agencies. And thank you very much for listening to my talk.